Thank you very much. Well, the first slide, actually, you can see a B-quad antenna. And yeah, you can see the scale. It's actually quite large because we are testing Wi-Fi mesh networking in Berlin in the 62 centimeter band. Who understands wavelength? Please raise your arms. Okay, well, it's quite a good audience. Excellent. Well, in front you can see one of the prototypes that I've built. But let's go into politics first. What you can see here on the slides shows the 2.4 gigahertz band. It's a trash band, or a garbage band, as they call it. We have 3 non-overlapping channels if we use Wi-Fi according to the 802.11b standard, which is now a legacy. But because we had so many devices that were following the US regulations of the FCC, actually many administrators of their networks, they only use channels 1 to 11 because that damn FCC gear cannot be switched to channel 13, which is legal in Europe under the ETSI. But these days, that's a proposal I want to make before we start. If you happen to configure a wireless network in a 2.4 gigahertz band, you should use channel 1, channel 5, channel 9, and channel 13, because these are channels that don't overlap if you use 802.11n or G. So, thank you. Thank you, because this way we can have 33% more bandwidth that we can all share. I think that's a decent proposal to make. But even though we have all these limitations and all these legacies, it's a very important infrastructure that we use every day. Like any reasonable media use today, it doesn't work with either Ethernet or Wi-Fi. You can only have frugal use, at least in Germany, where wireless broadband is very expensive and always capped. Yeah, without Wi-Fi, we would be, I don't know where we would be. And these days, the big mobile operators, they do something they call offloading. For example, if you're a customer in Germany and you subscribe to German Telekom, you have a DSL line, you might actually experience that there is an open access point called Telekom, which is in use by telecom users. They're sharing your internet bandwidth. Luckily, you get more than you pay for, so in order to cater for that. And by using this unlicensed band that is already overcrowded, the EU has estimated that this mobile offloading saves 84 billion euros each year. That's the figure for 2015, which is, of course, an estimation. But something has happened. You might have noticed that television in Europe and in many other countries is digital now. Here I have a picture. I took that from the New American Foundation. They're talking about spectral efficiency. In the EU, we used to have the analog PAL, television color standard, which uses 8 megahertz wide channels. These days, thanks to the spectral efficiency that has increased, because we have digitalized the television, and we all paid for that because we had to replace our receivers, we can accommodate 6 channels in one PAL channel. So in 8 megahertz of bandwidth, we can accommodate 6 television channels or 4 television channels and a couple of radio channels. So a large share of the spectrum has not been in use for a couple of years. What you can see here in this slide, the dark gray areas, there is 4 bands here in the US marked as used for broadcast television, Actually, the situation in Europe is there is 3 because we don't have this gap where it says wireless medical telemetry, at least not to my knowledge. And so today, we only need 1/6 of the bandwidth to have the same amount of programs. So we can reuse that for something that fits better into our time instead of simple broadcast. What I've just shown you is the spectrum, the whole spectrum below 1 gigahertz. And this spectrum has very interesting properties. If we look at the very high frequency spectrum, VHF and UHF, the wavelength is in decimeters. And wavelength, it matters. That's why I have this slide with this big wave. What will happen if this really big wave hits the surfer? Not much. I guess it's mildly affected. But what happens if a wave of the size of a glass of water hits the surfer? Well, the wave is cancelled out, mostly. And the same effect we have in radio physics. If you have a wave that is several meters long and it hits an object of this size, it's not affected much. If a wavelength of this size is hit or is hitting an oil tanker, for example, then it's cancelled out or reflected or broken. So, if we have longer wavelength, we can communicate better in case there are objects that are smaller than the wavelength. Unfortunately, in the 2.4 gigahertz band, our wavelength is only 12 centimeters. And in the 5 gigahertz band, it's even 5 centimeters. So very tiny. So any object which is sizable in relationship to the wavelength is an obstacle that breaks the wavefront. I have to explain that a little, maybe, to some of you. Wavelength, it's the length of the wave that it travels through space while it goes through one cycle. Here on the slide, there is a wave that cycles twice in 1 second. So the wavelength is 150,000 kilometers, give or take, because in the vacuum and in air, electromagnetic waves travel at light speed, which is 300,000 kilometers per second. Well, our waves that we use for Wi-Fi, they go 2.4 billion cycles per second, so they only travel 12 centimeters while they go through a full circle, and hence we have the wavelength. I hope this is quite a clear explanation. Well, maybe I shouldn't dive too much into that. Electromagnetic waves have an electric and a magnetic field, and as they travel through space at the speed of light, well, all those 3 properties are shown in this little slide. But let's not get confused by radio physics now at the first place. The consequence is that our experiment in Berlin uses 62 centimeter long waves, means that also our antennas tend to be quite large. In order to show it, I have a little demonstration here. This is a 2.4 gigahertz omnidirectional dipole antenna from a D-Link access point. It looks very tiny. That's because this antenna doesn't contain much air. Because these days, longer seems to be better. So the manufacturers, they have longer antennas, but basically there's just air inside. If you're lucky, the radiating part is a little bit higher in the plastic, so it's a little bit higher above the access point. So maybe you have a little bit better propagation properties. On the other hand, this is now Omni for the 62 centimeter band that we use for our tests in Berlin. So quite a difference, I must say. Here in the picture, you see an 8-element collinear dipole antenna that in theory gives a gain of 8 dBi. I'm not sure if that actually is accurate, but it works pretty well. So we have a resource that is now unused, at least at the moment, to a large part. But unfortunately, this resource is quickly auctioned off. And again, I have to say, unfortunately, this happened already for 2 large parts of the band in Germany. On the upper graph, you can see the spectrum that was auctioned first in 2010 to the big mobile telephone operators, Telefonica, Telecom, and Vodafone. And at a very high price. They paid billions of euros for that. And our politicians were celebrating that they generated so much revenue for the state. But that's a really silly claim to make, because probably we're going to try to use these services, so we will repay them for the investment that they made, and they want a quick return of their investment. So we have to pay for that. It's like an extra tax we pay on wireless broadband. And the lower picture is the auction that just happened in June 19th. For 5 billion euros, it was auctioned off to the 3 big mobile operators in Germany for a considerable amount of time. So, are we now all laughing all the way to the bank in Germany? Well, if we're bright, no. We are not going to do that, even though, yeah, some people think we are like sheep and tell us really silly things. Yeah, just if you're not from Germany, you're probably not that much interested in those figures. I'm not going to read it to you, but just to give you a quick overview what has been paid for. So what is wrong with that? Now only commercial providers, they get access to that resource. It's privatized, but it used to be public. If you consider analog television broadcast a public good. And we're promised that the market would handle our demands. But as we have seen in all those community networks, there is a big gap between the promise and reality, and it's very expensive if you're a user. So I have a different proposal to make, but that's not only me, that's also several others. We actually submitted a paper to the EU Commission suggesting that we should all have a dedicated license-exempt Wi-Fi band in the UFH range for everyone. Even the mobile operators, they can also do their mobile offloading there because it's free and open, can be used by everyone. They can use it as well, and they don't have to pay for. So we would all win. There is already TV Whitespace communication going on using a Wi-Fi-like protocol or a substandard of Wi-Fi, but it deals with databases. Before your device is allowed to go online, it has to request a database. So in order to get online, you need internet to get started first. And the problem is, in many areas, the database will simply tell you that you are not allowed to use that device. So actually, the situation in the United States is that people fake the geographic location of their TV Whitespace devices in order to use them illegally. The FCC is now demanding that, or has proposed, that the devices must have GPS built in, so the user is no longer able to fake the geolocation. They say since the devices cost $1,000 each, the GPS doesn't add much to the cost. Of course, $1,000 sounds a little expensive to me, but the devices that are on the market are mostly prototypes, and they're mostly software-defined radios because no manufacturer is making a chip dedicated for that band yet. And since the situation is very unclear, I don't know when it actually will come to us. Another problem with this use that TV Whitespace devices share a resource is that you could actually disturb the reception of other people that try to watch digital television or analog television for that matter. And if this proposal would be successful and we get at least a couple of megahertz, we would at least keep something of that private resource for the public. So there is not much on the market and it's very pricey. And since I like to eat my own dog food, I decided to build prototypes for that band. You can see the very first batch in this picture. I did it in a way by frequency converting. It's something that many hams are using. For example, when the 13 centimeter band was introduced into a ham radio, people used so-called transverters to use their existing gear from the 70 centimeter band or from any other band in order to shift it to the 13 centimeter band. And I'm doing the same by using multiplicative mixing. I'm going to explain that to you. Multiplicative mixing means that you have a local oscillator that generates a frequency. It's a transmitter. And an input signal is mixed with the local oscillation signal. And the output are mixing products. And you can see that in the next slide. New frequencies are generated from the input frequencies. I hope it's readable. I've made an example with some easy to calculate values. F1 is one of the frequencies, like the oscillator, and F2 is the input signal. If they are mixed by multiplicative mixing, we get two more signals at the output of the multiplicative mixer. We get frequency 1 minus frequency 2, and frequency 1 plus frequency 2. That's a very standard technology. Any modern receiver is working according to that principle because they all use intermediate frequencies. For example, if you have a FM radio and you tune that to 100.7 megahertz, if you have another receiver and you tune that to 90 megahertz, you will receive in close proximity to your radio a blank radio signal. That's the local oscillator of your FM radio because the intermediate frequency in FM radios is 10.7 megahertz, most commonly because there's filters exactly for that purpose with the bandwidth that matches FM radio. So you could actually receive transmissions from a receiver, which is funny. So in our example that we use in Berlin, we do exactly that. I have the figures here. I have this device, which is a standard Wi-Fi device operating on channel 5. That is 2,432 megahertz. And I mixed its output signal with 1,950 megahertz. And as a result, I get frequency 1 minus frequency 2, 482 megahertz, and an unwanted byproduct, which is F1 plus F2, but that's in the high 4 gigahertz range, and it is filtered out. So that's the block diagram of the prototype. On the left-hand side, you see the local oscillator. The frequency for up and down conversion has to be the same because the input and output channel needs to match in the receiving and in the transmission path. So there's two mixers, one for reception path and transmission path. And the output is filtered to remove the unwanted frequencies. Then in the transmission path, there's a driver, again a filter, which also does impedance matching for the PA, yet another filter and the RF switch, and then the signal goes to an antenna. And in the receiving path, the RF switch, of course, has to be switched to the receiving path. That is done by a GPIO. And then it's filtered, amplified, filtered, and mixed to the 2.4 gigahertz frequency again. And in our case, it's 482 megahertz that is present at the antenna. The circuit that I have designed is very widely configurable, so you can mix it to almost any frequency that is sufficient to carry the modulation of the Wi-Fi signal. Like you could operate it in the 50 megahertz range, for example. Which is good, because the FCC has come up with new regulations that new devices are only approved by the FCC if you are unable to install new firmware on it or modify the Wi-Fi driver. So you always have to be in their specs, but they cannot stop you from doing mixing like we do it here. Also, the approach of the FCC is very anachronistic because, well, you got a software-defined radio today that can broadcast anywhere between 50 megahertz and 4 gigahertz. And you should do some filtering if you amplify it, but then you can go to watts if you like, and the FCC can do nothing about it. Of course, it's not legal. Yeah, but well. So the actual implementation, the blue board that you see at the bottom, it's a Dragino 2. It's a device made by a guy in Shenzhen in small quantities. The name Dragino suggests that it's something like an Arduino, and it's quite hackable because it has GPIOs exposed. In principle, you can do what I have done with this device, also with other wireless routers, but then you have to take care for yourself how to get access to the GPIOs. But here they are exposed via a pin header. So I just designed a PCB that I could just plug in. I have a close-up so I can explain a little bit more in detail. So on the right-hand side, you see two antenna cables. That's where I take the TX and RX signal at 2.4 gigahertz from the Dragino. The little black stone below, that's the mixer chip. Very hard to solder for me in the first place. I had to learn quite a lot. And then there is the paths that I have explained in the block diagram. I hope I'm not running out of time. The result is, well, that's one of the first samples that I've tested. This signal that you see here is 802.11b, sending a massive amount of broadcasts. So they are at basic rate, which you can see if you're familiar with the modulation scheme at basic rate. And yeah, that's basically the same signal that comes in at the 2.4 gigahertz band. It's not perfectly clean because there is some overswing on the right side, but I checked it at the 2.4 gigahertz band. The signal looks quite the same. So I'm not messing it up so much. You have seen it on the first slide. That's one of the antennas that we use. That's a directional antenna, a B-quad. It's a very nice antenna, very easy to make. If you want to make a directional antenna for your existing Wi-Fi equipment, I would recommend it. This is a little bit larger, obviously because the wavelength is longer. And I've added this slide because where we assembled it on the church, you can only see it on the backside. This is actually the Zwingli Church in Friedrichshain. And below in the picture, you can see the B-quad broadcasting north. And since the wavelength is quite long, I didn't bother shooting through the window, which is already occupied by the 2.4 gigahertz gear, so we go straight through the wooden wall. Doesn't change much. Also, RF cable is really easy to handle, like the coax doesn't have a lot of attenuation. So you can use the cheap RG58. If you're into radio design, you know that, yeah, that the attenuation gets lower as you have lower frequencies and higher wavelength. And the result is, if you are radio aware and have some experience, you know about the Fresnel zone. That's just a little example of the Fresnel zone. If in the Fresnel zone you have trees and bushes, then those UHF waves, they pass through that quite decently. They will still be attenuated, but the attenuation is far away from the severe attenuation that you experience in the 2.4 gigahertz band, and far, far less than the 5 gigahertz band. I think you have experienced that before. If you try to connect to a 5 gigahertz network outdoors, if there is some bushes, you don't get far. You get much further at 2.4 gigahertz, and at 482 megahertz, for example, in the UHF band, the effect is even greater, so the range is even better. Very, very nice for an environment like here to have a broad coverage at a decent bandwidth, giving the same modulation bandwidth. The speed of the wireless network in the 482 megahertz band is exactly the same. That's my Fresnel zone at home. On the half to the right, behind all those trees, bushes, and metal fence, there is the church, and the signal gets through. It gets attenuated, still a great deal, but it's far away from the attenuation at 2.4 gigahertz. So I like it a lot, and we only have the license to use that for a limited amount of time. So I hope you could help me lobby a little for that we get a part of that spectrum for us all. Thank you very much. I hope you enjoyed the talk, and I hope we have some time for questions.
Yeah, you have actually 2 more minutes left. So if you have any questions, please line up at the microphones so we can tape them on the stream and everybody will hear them. Shoot out, please.
To what extent do you feel that the reduced attenuation at 482, given you're proposing an unlicensed band, which is not only going to contain Wi-Fi, it's going to end up containing program making for special events, radio mics, all sorts of stuff. That increased...
Sorry, can you say it again, because I couldn't quite understand correctly. You were talking about cordless microphones that operate in the UHF band?
Yes, what I was talking about was that at 482, you have less attenuation.
Sorry,
At 482 megahertz.
Yes.
You have less attenuation, so you're going to be able to accommodate less users in a given area.
Yes, that's a good point. There is a patch, it's called Minstrel Blues, which regulates the transmit power of Wi-Fi. At the moment, our Wi-Fi equipment at 2.4 and 5 gigahertz, it always broadcasts at the same power level. And by default, we all use full power. There's only a few people that are aware of that and that are limiting the power that they use. So, of course, that's a very good suggestion, because the range of the UHF band is far greater. It also means that the cellular structure that we use in order to cater for more bandwidth for more people or more devices in a certain area has to be taken care of. So my suggestion, and we also suggested it in the paper that we submitted to the EU, is that power regulation is mandatory. So, for example, if you can have a fine bandwidth to another node, if you broadcast at a very low transmit level, the device will automatically choose that. So, in order to reduce the interference that you can have with other networks. And I also like the idea to use this frequency for relatively long range coverage, so not necessarily for very, very high bandwidth. For example, in our prototypes, we can now use 5 megahertz, 10 megahertz, 20 megahertz, and 40 megahertz wide channels. And for example, if we decide to use the 5 megahertz wide channels, we can have 4 channels instead of 1, like we have by default in Wi-Fi, and at 25% of the bandwidth, which I think is a fair deal. And another very interesting property of this frequency band is that the polarization of the wavefront, it doesn't change so much. Like for example, if you have Wi-Fi and you shoot through a tree, then if your antenna is vertically polarized, you can also receive your signal horizontally polarized, because due to the wavefront getting broken in the leaves, the polarization is rotating. So you don't have a simple linear polarization. And that matters because if you have a straight linear polarized vertical electromagnetic field, and you try to receive that with a horizontal antenna, you will have an attenuation of 20 decibels. And so therefore you could very nicely separate the different wavefronts from each other, even though they are on the same frequency. So we can actually decide whether we use vertical or horizontal linear polarization or a circular polarization, but of course that's maybe a little bit too complicated to explain now. And we're running out of time.
Yeah, sorry, but the time is over. We have to shut you up.
Okay.
Sorry about that. It was a great talk. Please give a hands up. That's your applause.